Usually when you look at a textbook, especially if you are cramming for a major nursing board exam like the TEAS and the HESI, there's this expectation that science is just perfectly neat.
Right, it feels very absolute, just neatly categorized for our convenience.
Yeah, exactly. You memorize a list, you check a box, and you move on. But then you actually step into the physical world or, onto a chaotic hospital floor, and suddenly those neat little boxes are blown wide open.
Oh, completely.
So welcome to this deep dive.
Mhm.
Today, we have a very specific mission for you. We are tackling the states of matter. And to do this, we are taking a hefty... Right. So whether you are prepping for a medical entrance exam right now, or you're just insanely curious about the physics of everyday life, we're looking way past those standard dry definitions.
Setting that foundation is so important because when you understand the underlying mechanics, the actual why behind these scientific principles, memorizing them for an exam becomes practically effortless.
You aren't just reciting facts anymore. You are recognizing the fundamental patterns of nature.
Exactly.
We're going to uncover some tragic historical feuds, bizarre elements that absolutely refuse to follow the rules, and exactly why these invisible concepts are critical for literally saving lives in a clinical setting.
It's not just a list of facts. It is a guide to understanding the invisible machinery of the universe.
I love that. So let's start with the baseline definitions you absolutely need to know, and then we will immediately complicate things. Because nature doesn't actually care about our human-made boxes.
No, it really doesn't. But we do have to start with the big three.
The classical trio: solid, liquid, and gas.
Right. And to understand them, you just need to look at shape, volume, and particle movement. So a solid has a fixed shape and a fixed volume, and its particles are tightly packed, basically just vibrating in place.
Okay.
Then a liquid has a fixed volume, but a variable shape, meaning its particles can slide past each other fluidly. And a gas has both a variable shape and a variable volume, with particles moving freely and rapidly.
I always like to picture a music festival.
Ooh, that's a good one.
Right. So that solid is your tightly packed concert crowd right up against the stage. Nobody is going anywhere. They're just kind of swaying in place.
Mm-hmm.
The liquid is the crowd hanging out by the concession stands. It's still a defined group, taking up a certain amount of space, but mingling, taking the shape of the lobby area.
Right, sliding past each other.
Yeah. And the gas is when the concert is over, and the crowd disperses in a million directions into the giant parking lot, just filling whatever container they are in.
That is a perfect visualization for the exam. The state of matter is entirely dependent on a delicate balance between how much the particles are moving and how strongly they are attracted to one another.
But I have to push back a little on the textbooks here. Because we have a fourth state, right? Plasma.
Yes, the official fourth state.
It's an ionized gas full of free electrons and charged nuclei. But wait, if plasma makes up over 99% of the visible matter in the universe, like stars, the solar wind, lightning bolts, why is it treated like a footnote in grade school?
Well, it really comes down to human bias. I mean, textbooks give us a human-scaled snapshot of reality.
Right, what we see around us.
Exactly. On Earth, in our day-to-day life, we deal with solids, liquids, and gases. We don't interact with the interior of the sun on a daily basis.
Thankfully.
Right. But plasma is absolutely the universe's default state, and the naming of it is actually a fantastic piece of trivia that causes huge headaches for medical students.
Oh, I've heard this trips people up on exams all the time.
Constantly. So the term plasma for the state of matter was coined in 1928 by an American chemist and Nobel laureate named Irving Langmuir.
Oh, my.
He was studying ionized gases in vacuum tubes, and he noticed that the way the gas carried these highly charged particles reminded him of the way blood plasma carries red and white blood cells.
Oh, no.
Yeah. So he just borrowed the medical term.
Which is absolute nightmare for a nursing student trying to study.
It truly is. Exam writers love to exploit that overlap. So for you listening, make sure you explicitly separate physical plasma, which is the superheated state of matter, from blood plasma, which is the straw-colored liquid used in transfusions.
Right, they're entirely unrelated.
Completely unrelated.
We should also briefly mention the messy reality before we move on, because specialized physics recognizes dozens of states of matter beyond these four, don't they?
Easily. Yeah, when you push matter to extreme temperatures and pressures, the state of the substance is really about degrees of freedom and symmetry breaking.
Wait, hold on.
Yeah.
Degrees of freedom and symmetry breaking. What does that actually mean in plain English?
Okay, think of liquid water like a crowded dance floor where everyone is moving in random directions. Because it's chaotic, it looks pretty much the same no matter what angle you view it from. It has high symmetry.
Okay, that makes sense.
But when that water freezes into ice, suddenly everyone stops and locks arms into a very specific, rigid grid. You lose that uniform, look the same from any angle freedom. The symmetry breaks into a strict pattern.
Oh, wow. Okay. And then you get those exotic states too, right?
Yeah, things like Bose-Einstein condensates, which were first created in 1995 by cooling atoms to just a fraction above absolute zero.
That is wild. So if these classical states are the working model we know today, how did we figure all that out? I mean, moving from the what to the how takes us on this wild journey from ancient philosophy to a literal life or death scientific debate.
It is astounding how long human beings were completely wrong about this. I mean, trace the origin back to around 450 BCE. The Greek philosopher Empedocles proposed that all matter was built from four eternal roots: earth, water, air, and fire.
Which, ironically, maps somewhat cleanly onto our modern states, right? Like, Earth is solid, water is liquid, air is gas, and fire is roughly plasma.
It is a convenient modern mapping, sure, but fundamentally flawed in its physics. Still, Aristotle later systematized this four-element scheme, and it dominated Western natural philosophy for roughly 2,000 years.
2 millennia is a staggeringly long time for the entire scientific community to be completely wrong.
It really is. The major shift didn't begin until the 17th century when Robert Boyle published The Skeptical Chemist in 1661. He attacked the four-element theory and argued for a particle-based view of matter.
Right.
But the real breakthrough was the development of the kinetic theory of gases.
Okay, this is the theory that says matter is made of tiny particles constantly in motion.
Yes, so Daniel Bernoulli proposed in 1738 that gas pressure is just the result of countless molecular collisions. Then, in the 1850s to 1870s, James Clerk Maxwell and Ludwig Boltzmann mathematically matured this idea.
Okay, what did they prove exactly?
They proved that the state of matter is simply a competition between two things. First, kinetic energy, which is driven by temperature and pushes particles apart. And second, intermolecular attractive forces, which pull them together.
So temperature isn't just how hot something is. It is a literal measurement of kinetic energy. It measures how fast those microscopic particles are flying around.
Exactly. That is the mechanical reality of temperature. But this kinetic molecular theory was not accepted peacefully. It triggered brutal opposition, leading to the tragic story of Ludwig Boltzmann.
Wait, tragic. Telling the 19th century scientific establishment that matter is made of invisible, vibrating atoms didn't go over well.
To say the least. A powerful school of physicists and chemists known as the energeticists, led by Wilhelm Ostwald and Ernst Mach, completely rejected the existence of atoms.
Seriously.
Yes, their argument was that science should only deal with what can be directly observed. Since no one could see an atom, they considered them unobservable metaphysical fictions. They believed only pure energy was real.
Wow. Imagine trying to prove something you mathematically know is true, but having the most respected minds of your era mock you because the technology to see it doesn't exist yet.
The pressure and professional isolation were devastating for Boltzmann. He faced such exhausting rejection that he tragically took his own life in 1906.
Oh, that is awful.
And the terrible irony is that he was vindicated almost immediately after. Einstein published his paper on Brownian motion in 1905, and shortly after, Jean Perrin experimentally proved that atoms and molecules were physically real.
So he was right all along.
He was. Boltzmann was right all along, and his deeply contested work became the accepted foundation for everything we know about states of matter.
It really puts into perspective how hard-fought these textbook definitions are.
Absolutely.
Knowing that temperature is just molecular motion leads us directly to the next major piece of the puzzle, which is phase changes. When substances transition between these states, something very strange happens with energy.
Right, and you need to know the basic vocabulary first. So melting is solid to liquid, freezing is liquid to solid, vaporization is liquid to gas, condensation is gas to liquid, sublimation is solid straight to gas, and deposition is gas straight to solid.
Got it. Now here is the crucial exam concept for you listening. Basically, the secret of phase changes. Transitions involve energy transfer without changing temperature.
Yes. This is the most highly tested concept in this domain.
But I need a real-world sanity check here. If I'm boiling a pot of water on a stove at 100 degrees Celsius and I crank the burner dial to the absolute maximum,
Yeah.
the water itself doesn't get any hotter.
It does not. The water stays at exactly 100 degrees Celsius until
Wow.
it has all turned to steam.
Wait, where is all that extra heat from the stove going if the thermometer isn't moving?
It goes into the concept of latent heat, specifically the latent heat of vaporization. While a substance changes state, the added energy goes entirely into breaking the intermolecular bonds, things like hydrogen bonds and van der Waals forces holding the water molecules together in the liquid phase. Okay. The energy is spent tearing the molecules away from each other to overcome those attractive forces, not into raising the kinetic energy or temperature of the liquid.
It's like a toll booth. You have to
Yeah.
pay the energy toll to get into the gas phase, and until all the liquid water has paid that toll and evaporated, the temperature cannot go up.
That is a brilliant analogy. Yes. And this concept of latent heat has severe real-world consequences in medicine. It explains why steam burns are catastrophically worse than boiling water burns, even if they're at the exact same temperature of 100 degrees Celsius.
Because the steam is holding all that hidden toll booth energy.
Precisely. When 100 degrees steam hits your skin and condenses back into liquid water, it dumps a massive amount of latent heat directly into your tissue as those bonds reform.
Oh, wow.
Yeah, a boiling water burn only transfers the heat of the liquid. The steam transfers the heat of the liquid plus the massive latent heat of vaporization.
That is terrifying, but it perfectly illustrates how energy is moving around. This actually brings up a massive misconception we need to bust. The idea that cold is a substance that flows. Like when people say, shut the door, you're letting the cold in.
It's a classic trap. Cold doesn't exist as a physical entity. Cold is just the absence of thermal energy.
Right.
Heat always flows from high energy to low energy. If you hold an ice cube, the cold isn't creeping into your hand. The heat from your hand is rapidly escaping into the ice cube.
That is a direct application of the second law of thermodynamics. You can only move heat. You cannot move cold.
Correct.
Okay, so we have established the firm rules of physics.
Mhm.
Temperature is motion, latent heat breaks bonds. But nature loves exceptions. Let's look at the rule breakers and anomalies, starting with the most famous one, water.
Water is endlessly fascinating because it defies the fundamental rule of packing. Nearly every liquid becomes denser when it freezes because as the kinetic energy drops, the molecules pack tighter together.
Right, but ice, however, is actually about 8% less dense than liquid water. Liquid water is roughly 1.00 grams per cubic centimeter, but ice is about 0.92.
Exactly.
It's like putting together a piece of IKEA furniture,
Yeah.
and when you finally tighten the last screws, the whole structure suddenly expands to take up more space.
I love that. The culprit behind that expansion is hydrogen bonding. As water freezes, those bonds force the molecules into what we call a spacious, open, hexagonal lattice.
Meaning they arrange themselves in six-sided rings with a lot of empty space in the middle.
Yes. And the structural anomaly is the reason you and I are alive.
Because ice floats.
Right. If water froze bottom up like normal liquids, becoming denser and sinking, lakes would freeze entirely solid during the winter. Freshwater ecosystems would die.
Oh, wow.
Because it expands and floats, the ice on top acts as an insulating layer, allowing aquatic life to survive in the liquid water below.
That's amazing. Let's talk about another weird one. Dry ice, which is solid carbon dioxide. You can buy it at the grocery store, but it never melts into a puddle. It just sublimates directly into a gas at negative 78.5 degrees Celsius. Why does it get to skip the liquid phase entirely?
This comes down to a battle of pressure and something called the triple point. A triple point is the exact combination of temperature and pressure where a solid, liquid, and gas can all coexist in perfect equilibrium.
Right, and for water, that triple point is at precisely 0.01 degrees Celsius and 611.657 pascals of pressure.
Yeah.
It's so mathematically exact that it was actually used to define the Kelvin temperature scale until 2019.
But for carbon dioxide, its triple point pressure is about 5.1 atmospheres. At sea level, we only live in 1 atmosphere of pressure.
Okay.
Because our everyday atmospheric pressure is so far below CO2's triple point, liquid CO2 simply cannot exist out in the open. It has no choice but to go straight from a solid to a gas.
And a quick misconception check for you listening. When you see that spooky smoke rolling off dry ice, you aren't actually seeing carbon dioxide gas. CO2 gas is completely invisible. What you are seeing is the incredibly cold, dry ice chilling the air around it, causing normal water vapor in the air to condense into tiny liquid droplets. You're just looking at a miniature fog cloud.
Right, and these behaviors map onto phase diagrams, tracking states across temperature and pressure, proving that these aren't just weird parlor tricks, they are rigid mathematical laws.
Which brings me to one of my favorite myths to bust. I remember being told in school that glass is actually a slow-flowing liquid. The evidence they always cite is that medieval cathedral windows are thicker at the bottom because the glass is melted and pooled downward over the centuries.
It is a beautiful, poetic story, but it is entirely false. Glass is not a slow-flowing liquid.
So why are those old windows thicker at the bottom?
It is purely a manufacturing artifact. Centuries ago, window glass was made using the crown glass process, which resulted in uneven, rippled sheets.
Oh, I see.
When glaziers installed the glass, they obviously put the thicker, heavier edge at the bottom for structural stability. It has nothing to do with the glass flowing over time. Glass is an amorphous solid. Its atoms are frozen in a disordered arrangement, but it does not flow on any human timescale.
Okay, so knowing that glass is a solid, or that dry ice sublimates, is great for a physics test. But how does this save a patient's life on a chaotic ER floor? Let's move directly into clinical relevance, starting with pressure. We usually think boiling point is a fixed property like water always boils at 100 degrees Celsius.
That is a major misconception. Boiling point is heavily dependent on pressure. If you go to the top of Mount Everest, where atmospheric pressure is roughly a third of what it is at sea level, water boils at around 70 degrees Celsius.
Which means it takes way longer to cook pasta on a mountain because the water can't get hot enough.
Exactly. But in a clinical setting, we go the other direction. Hospitals use autoclaves to sterilize surgical instruments. An autoclave is essentially a reinforced pressure cooker. It actively raises the pressure inside the chamber above normal atmospheric pressure.
So because the pressure pushing down on the liquid is higher, the water has to fight harder to turn into a gas.
Precisely. The water doesn't boil at 100 degrees. It stays liquid until it reaches much higher temperatures. And it's that extremely high temperature pressurized steam that effectively creates a lethal environment to sterilize the instruments.
Wow, you are manipulating the physical state of water to kill bacteria. What about the gas laws?
Gas laws are everywhere in medicine. Hyperbaric oxygen therapy and anesthesia delivery completely rely on the relationships between pressure, volume, and temperature. Specifically, Boyle's law, Charles' law, and Avogadro's law. You have to know how gases will behave when compressed or heated to keep a patient stable.
Imagine you're standing in the ICU looking at an arterial blood gas readout, an ABG. Nurses are constantly looking at BO2 and PaO2 values. How exactly does a physical law translate to interpreting a patient's chart?
They are literally applying Dalton's law of partial pressures. Yes. Dalton's law states that gases in a mixture behave completely independently of each other. The oxygen acts as if the carbon dioxide isn't even there, and vice versa. Each gas exerts its own partial pressure that adds up to the total pressure.
So if a nurse just looks at the total pressure in the blood, it might look completely normal, but they could be missing a crisis.
Exactly. If a patient's carbon dioxide levels are dangerously high, pumping them full of oxygen doesn't magically push the CO2 out because the gases are interacting like that.
Wow.
If a nurse misreads this and assumes total pressure tells the whole story, they might oxygenate a patient who actually needs CO2 clearance. Without understanding the independent partial pressures, interpreting an ABG is just guessing. You have to know the physics to understand the physiology.
It is all incredibly interconnected, even with something like cryotherapy, where you use liquid nitrogen at negative 196 degrees Celsius to freeze off skin lesions, or using dry ice to ship vaccines around the world without a liquid mess melting in the cargo hold. You are using the principles of phase changes and sublimation as vital medical tools.
I will reiterate one final time for anyone prepping for their exams. When you are answering questions about these clinical scenarios, be incredibly careful with the word plasma. Don't let an exam writer trick you into confusing a superheated ionized gas with a blood transfusion.
A vital warning. Okay, let's bring this all together. Instead of just reading down a list, let's look at the underlying story these facts tell us.
I'd say the biggest takeaway is that energy and temperature are not always the same thing. During phase changes, a substance absorbs or releases energy, that latent heat, to break or form molecular bonds without changing the actual temperature on the thermometer.
And those bonds can create incredible anomalies, like hydrogen bonds forcing freezing water into an open hexagonal lattice, causing ice to float and saving freshwater ecosystems.
We also saw how manipulating pressure allows us to bend the rules. Lowering pressure at high altitudes lowers the boiling point, while raising it in an autoclave creates superheated steam for sterilization. And if everyday pressure is low enough, like with dry ice, a substance will sublime, skipping the liquid phase entirely.
Finally, despite our earthly bias toward solids, liquids, and gases, plasma reigns supreme, making up over 99% of visible matter in the universe.
It really challenges our perspective on what is normal in physics.
Which sets up one final thought. We started by saying that science isn't always neat, and that nature doesn't easily fit into our human-made boxes. Nothing proves that more than a concept we haven't even touched on yet: supercritical fluids.
Oh, this is a fascinating phenomenon. Industries use supercritical carbon dioxide to decaffeinate coffee.
Really?
Yeah, they do this by pushing the CO2 past its critical point. They crank up the temperature and pressure so high that the boundary between the liquid and gas phases completely dissolves. The two states become entirely indistinguishable from one another.
That's crazy.
The substance has the density of a liquid, but expands to fill a container like a gas.
It's a state of matter that violently refuses to be categorized, so we leave you with this to ponder. If temperature and pressure can be manipulated to blur the lines of physical reality so thoroughly that the words liquid and gas no longer mean anything at all, what does that say about our human need to force nature into neat, organized little boxes? Keep questioning, keep learning, and we will catch you on the next deep dive.